cosine of x as a Maclaurin series. Recall that the Taylor series is the series of the form the n derivative evaluated x equals a over n factorial times x minus a to the n. So we would need the derivatives. Let f of x equals cosine of x. The first derivative is negative sine of x. The second derivative is negative cosine of x. The third derivative is positive sine of x. The fourth derivative is cosine of x, and the fifth derivative is negative sine of x, so the cycle repeats. Since this is the Maclaurin series that we are seeking, we're going to evaluate these derivatives at a equals 0. f of 0 is cosine of 0, which is 1. f prime of 0 is negative sine of 0, which is 0. f double prime of 0 is negative cosine of 0, which is negative 1. f triple prime of 0 is sine of 0, which is 0, and the fourth derivative evaluated at x equal to 0 is 1, and the fifth derivative is 0. Observe that all the odd derivatives are 0 out, and the even derivatives are either 1 or negative 1, oscillating between 1 and negative 1. The coefficients in the Taylor series are therefore c sub 0 is 1. C sub 1 is 0 over 1 factorial, 0. C sub 2 is negative 1 over 2 factorial. C sub 3 is 0. C sub 4 is positive 1 over 4 factorial. C sub 5 is 0, and so on. And so cosine of x is 1 plus 0x minus 1 over 2 factorial x squared plus 0x cubed plus 1 over 4 factorial x to the 4th power plus 0x to the 5th, and so on. Simplifying this to get 1 minus 1 over 2 factorial x squared plus 1 over 4 factorial x to the 4th minus 1 over 6 factorial x to the 6th, and so on. We see in a pattern to write this in a sigma notation. The denominators are even, 2n factorial. The power is also even, x to the 2n, and this is an alternating series, negative 1 to the n. Thus, cosine of x is the series negative 1 to the n, x to the 2n over 2n, the quantity factorial. We assume that cosine of x has a Taylor expansion. We still need to show that the remainder is 0. Notice that the n plus 1 derivative are either plus or minus cosine of x or plus or minus sine of x, but the absolute value of these are always less than 1. And so the Taylor inequalities states that for all the absolute value of x less than a number d, the remainder is less than or equal to m over n plus 1 factorial times x to the n, but m is 1 over n plus 1 factorial x to the n plus 1. We take the limits of this as n go to infinity, it is 0. X is a real number, n go to infinity. To find the interval of conversion, we use the ratio test. With the a sub n terms is negative 1 to the n, x to the 2n over 2n factorial, and a sub n plus 1 is x to the 2n plus 1 over 2, we replace n with n plus 1. And so a sub n plus 1 is x to the 2n plus 2 over 2n plus 2 factorial. The limits of the ratio of a sub n plus 1 over a sub n is therefore the limit of the absolute value of x to the 2n times x squared over 2n plus 2 times 2n plus 1 times 2n factorial. Multiply the reciprocal of a sub n, which is 2n factorial, over x to the 2n. Simplifying x to the 2n and 2n factorial, we end up with x squared over 2n plus 2 times 2n plus 1. Note that we ignore the negative 1 to the n because of the absolute value. This limit is 0 as n go to infinity, and so x squared times 0 is 0. This limit is always less than 1, so by the ratio test, the series converges for all x. Thus, we conclude that cosine of x is the Maclaurin series n go from 0 to infinity of negative 1 to the n, x to the 2n over 2n factorial for x between negative infinity to infinity, all real numbers. Once we have a series representation for cosine of x, we can integrate term by term to get sine of x. Sine of x is a series. Negative 1 to the n is a constant. 2n factorials in the denominator is a constant. The antiderivative of x to the 2n is x to the 2n plus 1 over 2n plus 1. But the denominator is 2n plus 1 factorial. And so we obtain a series representation for sine of x. If we want a series representation for sine of x squared, then we use sine of x, replace x with x squared. X squared raised to the 2n plus 1 over 2n plus 1 factorial, and simplifying this to get the series negative 1 to the n, x to the 4n plus 2 over 2n plus 1 factorial.